Our speaker today is Captain Carl Winter. He is the commander of an ocean-going cable-laying vessel, and he will speak to us about his experience in that area. Captain Carl is from Wayne, New Jersey, and attended the United States Merchant Marine Academy at Kings Point, New York. He spent the first years after graduation competing on ocean racing sailboats internationally. He then worked on various types of commercial vessels, including tankers, tugs, and freighters. Captain Winter then joined the Transoceanic Cable Ship Company in early 1992. And at the time, that company was a wholly owned subsidiary of AT&T. Since then, he has worked for Transoceanic, installing and repairing telecommunications systems worldwide, as well as supporting various subsea scientific projects built on fiber optic backbones. Captain Winter served in the U.S. Naval Reserve and attained the rank of Lieutenant Commander. And he's also a former member of the Sea Scouts Ship 104 in Wayne, New Jersey, many years ago. Welcome, Captain Carl.
Thank you, Ian. Favorite vacation spot? Home. Anyway, Ian didn't tell me I was following a Harvard PhD in the speakers campaign here, but I'll try my best. Again, as Ian said, I grew up in Wayne. I don't know if anybody's been through Wayne. There's a little lake called Packanack Lake. It's about the size of this room, maybe a little bit bigger, John, but tiny little mud puddle that a lot of us grew up sailing. We've actually had a couple sea captains, a couple international competitive sailing racers come off of that lake. So a lot of it is because of Sea Scout Ship 104. John's predecessor running the group was a guy named Dave Manazian, and Dave really brought the love of water and the sea to the youth of Packanack Lake and really spawned a love of traveling the world on the water. So that's how I ended up doing what I'm doing. Again, as Ian said, I attended the United States Merchant Marine Academy at Kings Point, which is one of the 5 federal academies, Naval, Air Force, Army, Coast Guard, and Merchant Marine. As far as my career, again, I mean, Ian summarized it. I can sit down now, but I've worked on everything from small sailboats to large ocean-going tankers, and I've spent the last 30 some odd years working in a little niche in the industry, cable laying. It's actually booming right now. I've already talked to a few people that are out there in the audience. Fiber optic cable laying is going gangbusters right now. So I did put together a little bit of a PowerPoint here on the cable laying industry. So undersea cables. The world is connected by threads that run across the ocean bottom. And I've got some samples up here if somebody wants to grab them and start passing them around. But cables across the ocean. This started back in the late 1800s. The first telegraph cables were spanning Europe and spanning North America. And the fastest way to get a message from California to Europe was telegraph across the country. And then the shortest sailing distance was from the Canadian Maritimes across to England. So they used to have telegraph cables all the way to the Canadian Maritimes, put your messages on a packet, send it across to England, and that's the way you could get a message to Europe. Somebody decided in the late, or actually the mid 1800s, that maybe they could come up with a scheme of running a telegraph cable across the Atlantic. And there were some players in it. Cyrus Field from the United States, being one of the main backers, decided that this was needed. So the first transatlantic cable was installed in 1858. It was a failure. They lost a lot of money. It lasted 3 weeks, and it could send one character, not one word, one character every 2 minutes. Some of you characters may have taken a little bit longer, but they tried again, 1866, 8 words per minute. So they upped the speed. I mean, we talk about communication jumps along the way, one character every 2 minutes to 8 words per minute. That one was actually a success. So now they had pretty reliable communication across the Atlantic. Once that was done, the cables really started spanning all over the world. I was just working off the coast of India earlier this year. We pulled up one of the first telegraph cables that was from that area. Once the Atlantic was spanned, they then went from the UK down the English Channel, or across the English Channel, down the Med, down the Red Sea, across the Indian Ocean, ringed India, and then across to Singapore. So now the British Empire was covered with telegraph communication. And what it used to take Queen Victoria 3 weeks to do, send a message from London to Mumbai, now took 3 minutes. So it was really a dramatic revolution. A lot of these cables are still sitting on the bottom. As we were installing new cables, we had to clear the route that we were using to install a new cable. So we pulled up some telegraph cable from the late 1800s. Fast forward a little bit, telegraph was great, but then Alexander Graham Bell got involved. Telephone, people wanted to talk. It still took quite a while from the span of 1866 to the 1950s until the first telephone cable went across the Atlantic. And it was very limited in its capacity. A few voice conversations, 36 voice conversations simultaneously. So that's why, if we remember, if you wanted to call internationally, you might have to wait in queue for a while before you could get a voice circuit to Europe. Took a while. Bell Labs started playing around with fiber optics in the late 70s, early 80s. One of the first cables of any distance was actually in the Canary Islands. It was basically a beta test of fiber optics, went between the Canaries and Spain, fairly short haul. That was done in the mid 80s. Everything was developed. They worked the bugs out. And then there was a consortium between a couple European cable companies and AT&T, and they put the first fiber optic system across the Atlantic in 1988. Anybody here have a house on Long Beach Island or ever been down to Long Beach Island? Yeah. TAT-8, which was transatlantic telephone number 8, the first fiber system, actually crosses the bay from Tuckerton, comes across right near Bay Village in Beach Haven, across the island, and then off to England. There are actually several cables that cross Long Beach Island, some of the old analog cables and some of the newer fiber cables. Tuckerton is a big cable landing station, control station, where the cables actually meet the backhaul of the terrestrial systems. That first fiber optic system, I worked on this system, not on the installation, but on the repair side. This was put in 1988. It had a service life of 30 years, and it was 40,000 simultaneous voice conversations. So we went from 36, the analog cables got better and better. The last analog cable that AT&T was involved in was 1985, again, with a projected 30-year service life. 3 years later, they put in the first fiber system, 1988, with a 30-year service life. Every generation of cable since then, just like your laptop, your phone, your television, it has made the last generation basically redundant. because the technology has grown in leaps and bounds. 1985, the last analog system, 30-year life, that was shut off. I believe it was 1994. They shut it down because it just couldn't handle enough circuits to make it worthwhile to maintain and operate. TAT8, the first fiber system, actually is intact. It's still on the bottom. It would work if they turned it back on, but same thing. They shut that down around the year 2000 because each generation of cable made the last one redundant. Nowadays, we don't even talk about voice conversations anymore. If we wanted to talk on the phone with modern satellite technology, cables would be redundant. We wouldn't need them. Phone conversations isn't what we do. If we flipped back to everybody wanting real-time Zoom calls, moving their data around the planet, that's why fiber optics exist. So we're now talking about 200 terabits of data moving through a cable at the speed of light, or virtually the speed of light. Terabyte is 1,000 gigabytes. Some of you technology people could probably go into depth of the amount of data that is, but hundreds and hundreds of millions of voice calls, if that's what we wanted to do. So these cables really, we went from telegraph, 50s and 60s, into the 70s, satellites were becoming more popular. But then when the fiber optic revolution hit, the cable industry really bloomed again. And I was saying earlier to a few people in the audience that like the Atlantic is one area where there's a plethora of cables going across. If you just want to move a lot of data, there's plenty of cables. But now everybody wants to move their data faster. The signal travels at the speed of light, but there are processing delays. There are some amplification delays. So the goal now is to move that data as quickly as possible. So in certain areas, it's all about making a cable system that moves the data faster. In other areas, like the system that I was just working on, it's about wiring up places on the planet that may not have the same data movement as transatlantic. So the last job I was working on, which is still ongoing, is a cable that spans the distance from Marseille in France to Singapore. And it's done for a company in India. So the cable starts in Marseille, couple landings in the Med, one in Italy, one in Greece, down to Egypt, jumps the land bridge across Egypt, and then down the Gulf of Suez, Red Sea. There's a landing in Aden, Yemen, another planned one up into the Persian Gulf, then over to Mumbai. And then from Mumbai, India, runs down the coast, connects up the Maldives, Sri Lanka, a couple more landings in India, jumps over to Malaysia, and then Singapore. So that's a project my company Subcom is working on right now. We've currently got 3 ships involved in that. So that's just a little bit of the history of cable laying and some of the stuff that's going on now. Again, not quite best map, but Africa, Europe, South America. So you can see in the Western Hemisphere, there's a huge capacity across the Atlantic, obviously, New York and the US data centers, government centers, financial centers to the European centers, and then wiring up the rest of the world. Years ago, AT&T, when I first started back in the early 90s, had a great program where they wanted to connect Africa. They courted the South Africans because at the time, the South Africans were one of the few countries in Africa that had the infrastructure to support technology like that, and also the money to finance it. The South Africans basically said, you're talking about building a cable system to connect our cities, but even in South Africa, our cities don't have the infrastructure to put that signal out to the rest of the country. We're not interested in financing that. Give us a chance to catch up. And that was a lot of the developing world. There was a lag of wiring up with the high data fiber optics because there just wasn't the backhaul into the interior of the countries. the wireless revolution came about. You didn't have to build wires, poles, set up all that infrastructure, set up a couple wireless poles in certain areas, and your country's covered. Move the data to the country and then use the wireless to disperse it. So now around the world, a lot of those places, some of the smaller countries, some of the smaller locations, less technological need, are now being wired up with fiber optics and then using the wireless backhaul to get it to the population. And again, just another map of submarine cable systems around the world. Everything is pretty well covered, but as I said, what you built 5 years ago is probably outdated today. Your operating cost, because you can sell more to more customers with higher capacity, faster speeds, hence new cable systems being installed. Also, when I started in the industry, your customer, your owners of the cable systems were the traditional telecom companies, AT&T in the US, British Telecom, Cable and Wireless, France Telecom, Telefonica of Spain, Telefonica de España. They would get together, form a consortium, say we need a new cable in a given area. Cable would get built, capacity would be sold, and that's the way the world worked. 1990s rolled around, the dot-com revolution, people looking at moving data, a lot of money floating about, investment bankers got involved, and we started to see independent companies building cable systems and then selling their capacity to non-traditional telecom companies. Of course, we all know what happened with the dot-coms. They crashed. Some of these companies that survived actually looked around and said, why would I buy capacity from you when I can just buy you? So in some cases, they bought some of the traditional telecom companies, or they bought up this plethora of systems that were being installed to support the dot-com revolution that now had no customers. So enter the non-traditional telecom players. Nowadays, one of our biggest customers at Subcom is Google, because Google says, we don't have any presence in New York. That's not where we do business. That's where our customers are. But our data center is somewhere else. They've got a data center in Bilbao, Spain. They've got a big data center down in Virginia. So they said, we want a cable from Virginia to Spain. We've actually done, we're on the second Google cable from North America to South America. We've done 2 across the Atlantic. We've done 2 across the Pacific. We also see Facebook as an investor, not so much just to support their platform, but again, Mr. Zuckerberg has tucked a few shekels away and he wants to invest them in new infrastructure, something that's going to make him money. So he's invested in cable systems. Amazon, and the first time I ran into somebody from Amazon on the ship talking about a cable, I said, how are you going to send packages? And they said, yeah, data packets, not packages, and we're just looking for the investment. So again, Bezos is looking for, when we don't want somebody to drop off a widget and, on our front porch in 10 minutes after I order it, but looking to support what the future is. So those are the non-traditional telecom companies. And it's gotten to the point where even some of the big telecom companies are sitting back and saying, let them build. When they build, we will come. If we want to buy capacity in a certain area, we don't want to invest in a cable system. Let's see who else did it. And of course, we can buy capacity off of them. So the business is booming. It looks a little bit different than it used to, but cables are still the way our data moves around the planet. And again, I talked about capacity, how much data can you move, and then how fast does it move? Goal 0 in the industry is actually moving it at the speed of light. Never quite get there because of the processing delays, but that's what they're chasing. The shortest route, we actually did a job for a company that was building a cable, or they wanted a cable built to run from North America, the financial centers of New York and Canada, to London and the financial centers of the continent. They wanted the data to move as fast as possible. So not only did they want the fastest cable, they wanted the shortest route. So like the old telegraph cables that went up to the Canadian Maritimes, the terrestrial backhaul for this cable went up to the Canadian Maritimes, and then the fiber optic jump went from Halifax across to London. Virtually every other cable in the area always went from that area, dipped south of the Grand Banks, and then ran across the Atlantic. They said, no, we want the shortest possible route. So as we're out there installing this cable, we have a couple tools that we use to bury the cable in the seabed to protect it. And those systems have cameras on them. And we're looking at the seabed and we see scars going across the seabed. Normally that's where you see fishermen dragging their trawls. We had a local Canadian fisherman on board and we said, look, there's some trawl scars here. We're glad we're burying the cable. He looked at the cameras and said, those aren't fishermen. We said, well, what else would make a scar here? He said, that's icebergs. He said, the big bergs will actually run aground out here. He goes, your cable, it's not a when, or sorry, it's not an if, it's a when that is going to be taken out by an iceberg. So that was why traditionally all the other cables ran around the Grand Banks, because in our world, it was shallow water. It was about 50 meters deep, 150 some odd feet. And he's saying that there are icebergs out there that ground in that water depth. Thankfully, when we were doing that job, we did not see any icebergs, which when I mentioned to somebody in St. John's, Newfoundland, that we spent the entire summer on the Grand Banks and we didn't see an iceberg, they said that was impossible. I said, no, it was a matter of fact. We saw no icebergs. Most days you couldn't see your hand in front of your face because it was so foggy. Saw plenty of them on radar. We actually had a fishing boat that was working with us that we would send out periodically to sit next to an iceberg and make sure it was drifting away from us. We also contracted a system that overflew the area every day in aircraft using a heat signature system and also something called LiDAR, a laser system, to track the icebergs. And that system existed not so much for the work we were doing, but just off the Canadian Maritimes are some oil and gas platforms, which can't move. So they'll actually keep some huge tugboats on standby. And if they see bergs heading towards them, we'll send the tugs over, they'll drop a rope around the berg and just try to gently nudge it out of the way. They don't have to go far. A miss is as good as a mile if you're talking about an iceberg hitting you. But that cable system was called Hibernia Express. One of the other interesting things about that system, and I again mentioned a few people earlier, when you start talking about data security, the company that originally won that contract for the manufacturing and installation of that cable for that customer was a company called Huawei, Chinese company. When the system owners applied for the licensing to have that cable system run from the data centers of New York to the data centers of Europe, all the regulators said, Chinese technology? No. So it was actually one that I think we were the second in the bidding process. It got awarded to the Subcom consortium that we were working with, and we won that contract because the regulators did not want Chinese technology involved with our financial systems. So just a few little facts. These are some Subcom facts. Subcom actually is a legacy company. Ian mentioned the company that I actually work for is called Transoceanic Cable Ship Company. We were a wholly owned subsidiary of AT&T Long Lines. I heard there's a few of you that were in the Bell Labs systems. AT&T, Bell Labs was all headquartered here in New Jersey. If anybody ever drove through Chester out near the telephone farm, where they had the telephone poles that they had up for testing what was the best for telephones. They're actually up on top of the hill. There was a structure that is gone now, unfortunately, because it was part of history. It was called the Cable Ship Fantastic. And Bell Labs did a lot of their early development and basically development and proving of the systems that we still use for high-speed laying of cable on a hill in Chester, New Jersey. When I started with the company, our queen of the fleet was the Cable Ship Long Lines. She was built in 1963. She was the AT&T Long Lines Division cable laying ship that was active from 1963 until 2003. Since then, we've built on that same idea, modernized the platforms, but a lot of the same basic technology. As a matter of fact, I'll get into some of the specifics, but back in 1860, as the ships were going across the Atlantic laying cable, they were keeping track of the tension on the cable so they didn't break it. They were keeping track of how fast they were going and how fast the cable was paying out so they didn't over tension it on the bottom. And if they had to retrieve a cable from the bottom, they lowered a hook on a rope, dragged it along the bottom until it snagged the cable. Rope got tight and they picked it up. We still do the same thing. Technology has come a little bit further, and I'll get into that in a minute, but a lot of the stuff that we use, and I joke around all the time, we're using 1860s technology in the 2000s. But again, with Subcom, we've installed enough cable to go around the earth 17 times, over 200 different unique cable systems deployed. Some of them are short haul systems. Cyprus to Israel was one short haul system. It's a unique system. And then like one I just spoke of, going all the way from Marseille to Singapore, or Oregon over to Australia. Little quality, 100% were delivered on time. You can change when they're due. On time is always one that anybody that's worked in manufacturing and process, sales is over here. The guys at the end who are actually doing the delivery are over here. Sales process promises one thing. With us, it's not only manufacturing. Maybe you have a glitch in manufacturing. Maybe sales said, we're going to do this. And it gets to the whiz bangs and they said, you told them we were going to do what? So a lot of the architecture of putting a signal on a piece of glass and sending it across the ocean, that's where the black magic comes in. I'm not going to try to tell you how it works, but it does. And we also have Mother Nature. You ever run into Mother Nature sailing around the world? Force 4. My best was a cable repair off the Canadian Maritimes in a Rising Force 9. Was not fun. Rising Force 9 is coming on hurricane strength. We actually, in that instance, were repairing a system. It was another customer's components in the system that were failing. So we had to go out and replace a bunch of amplifiers so that the system would work. We were contracted to do this. Of course, it was the middle of winter in the North Atlantic, and the weather was not exactly cooperating. We went from what should have taken us about 10 days, took us about 45 to get done. We ended up having to just cut the cable twice because the weather forecast, actually, if you guys been paying attention to Al Roker the last couple of years, talking about something called a bomb cyclone, where the weather systems just explode. Well, when it happens in the middle of the Atlantic Ocean, it gets interesting very quickly. So we had a bomb cyclone. I got one weather forecast and it was for uncomfortable. And the next weather forecast was hurricane force and 40 to 50 foot seas. We can work in rough weather, but we can't work in that. So I had just talked to the guys that were splicing the cable that we were fixing and said, cut it. And they said, we just put 12 hours into this job. I said, cut it. We got to run. And after the cyclone hit, I was talking to our weather forecasters. I said, where can I go to get some relief from this weather? And the guy I was talking to, comedian, says, you can go south of Cuba, or you can go up in the Laurentian Channel, up in the St. Lawrence. He goes, but up there, you'll be covered with ice in a couple hours. So I would say head south. So we did. So this 100% on time, sometimes the time gets stretched a little bit, but again, the sales guys have said you'll have it in by June. Sometimes we start in June. One of my colleagues was working on a transatlantic system. He spoke to the same weatherman. This was sometime in November. He said, when do you think I'm going to get a clear bit of weather to do this? And the guy said, May. So I think they finished it in November. Let me back up this one moment. Optical repeaters, I'll talk about those in a minute, but when we start with the cable system on one side, as we go across the span of the ocean, that signal needs to get boosted. So every 45 to 90 kilometers, and we do everything in the cable world in the metric system. So every 45 to 90, every 30 to 70 miles, we actually have to have an amplifier to boost the system. So we've put in over 7,500 of these units around the world. The Great Eastern, Isambard Kingdom Brunel, who was one of the whiz bangs in the Industrial Revolution back in the UK, built a ship called the Great Eastern. Commercially, it was a flop in many ways. It was just too big. They didn't have a lot of use for it. It was a steam paddle wheeler with sails, and it just, it didn't do a lot of the business that they thought it was going to do. But one of the things that it lent itself to was they converted it into a cable laying ship. They put some tanks inside. They put the early cable laying machinery on deck, and they actually used that ship to go across the Atlantic in 1866 and lay the first successful transatlantic cable. Navigation systems on that. Everybody's got a GPS on their phone now. We were driving back from Massachusetts yesterday, following the navigation system, came to a crossroad. It said, turn left, took us into a Costco parking lot. And there were dozens of cars following the same loop because it said, go that way. So it knew exactly where we were and told us where to go. And then I told it where to go. But back in the day, these guys were using celestial navigation. And going across the North Atlantic any time of the year means that you might not know exactly where you are for days at a time, because you might not get a clear sun sight or a clear star shot. So you're doing dead reckoning navigation, and they managed to do it. I'll digress a little bit. And we never worked on the cables of that generation, but when I started, we were still working on and repairing some of the early telephone cables that had been installed in the mid 1960s. 1965, your mid-Atlantic navigation systems really were not all that much better than what they were using in 1866. So if we were going out and looking for a cable to repair in the middle of the ocean, we would start miles from where the installer said they were when that cable went in. And what I mean by start is we would pick a location, we'd lower a hook to the bottom on a long rope and start dragging it until the rope got tight. And then we would hope that we got the cable that we wanted to. So if it was laying on the bottom, the first move was actually drag that hook that had blades in it and cut the cable into two pieces, because there's not enough slack in it to get it to the surface. But we'd have to cut it into two pieces, go back with another set of hooks, fish for one end, get it to the surface, test it, make sure that whatever damage or component failure was in that segment, make sure it wasn't there. If it was all good, we'd seal it off, lower it back down to the bottom on a buoy system, lay out some rope along the bottom, an anchoring system, and then a surface buoy. And this might be in 4,000 to 5,000 meters of water. So we're talking miles of rope just to get that buoy to the surface, go around, fish for the other side. Same thing, get it up, clear the damage. Now we have 2 bits of cable at the surface. We end up having to splice in twice the depth of water because we don't send people down to do a splice. We actually get both bits to the surface, splice in a new section of cable, go back, pick that buoy up, get that other end up, do the splice on the surface, and then lay it back down on the bottom. Something that was installed in the mid 1960s. As I said, we start miles from where that cable was installed because kind of a crapshoot. Unless somebody in modern times has touched that cable, you're not really sure where it is. You know, fast forward to today, GPS technology, I'll get into it in a little bit. We use a system called dynamic positioning. When we're in the middle of the ocean, if I've got solid GPS connection, I can hold the ship steady in position in less than a meter of diversion. So from you to I is twice what I would allow if I really wanted steady positioning. So when a modern cable ship says we're here, that's where they are. We might start a couple hundred meters from that cable position, doing the same thing, dragging a hook or sending a remote submarine down to find that cable. But that was the how way back in the 1860s. This is actually one of the ships that I worked on last year, the Reliance class. Subcom built 6 of these. We've got 6 sister ships, plus an older ship that was built in the early 90s, which was actually my first ship, and then another ship that we've just purchased. So we're running a fleet of 8 ships. 6 of them look like this. Reliance class, 465 feet long, maximum of 80 personnel on board. Back on the stern area is actually where we do all the cable laying. We've got a big gantry that can lift one of our tools for burying the cable called a sea plow, lift it off the back end of the ship. I spoke of those buoys that we use when we're lowering a cable in down to the bottom. Kind of hard to see, but that's a buoy capable of supporting a mooring system in up to about 9,000 meters of water. So 7 miles of water depth. Generally, the deepest that we try to work is about 7,000 meters. Some of the lighter weight cable systems, if you go deeper than that, they actually won't support their own weight if you have to go back and try to retrieve them from the bottom. Because if we hook them, try to lift them to the surface, we may have twice the depth of water hanging on a set of hooks. Just the weight of that cable in the water would cause it to break on the hooks. So there are some limitations to where we can go, but 5,000 to 6,000 meters of water is normal for us. Another little fact on water depth, when we're laying cable on this ship, we're installing our lightweight cable product. This is what's laying on the seabed. This is actually a slightly older generation. It's 21 millimeters in diameter, so it's just a little bit less than an inch. Oh, sure, there we go. And this is what it looks like when it's opened up. So there's a glass fiber package in the center, steel wires to give it strength, a copper sheathing to provide power to the amplifiers, and then a high density polyethylene coating. But when we're laying this product, the newer is slightly less diameter. It's 17 millimeters in diameter. If we're laying this in 6,000 meters of water, it's going over the stern of the ship. The ship is moving along at 7 knots maximum speed, 10 miles an hour-ish. That cable is leaving the ship, but it's actually not touching the seabed until about 25 kilometers behind us. As we're moving along, that cable has a nice angle down. It also develops a catenary to the point where when we're at that speed and we've got that amount of cable in the water, if we just stop the ship, that cable continues to sink and it will eventually break because it can't support that amount of cable at the ship end just due to the weight of the cable. So if something happens, if we have a quick slowdown or a stop, we have to immediately start backing the ship up at the known sinking rate of the cable. So little games that we play to make sure that we're doing a quality installation. Cutaway view of the ship. So again, this is the Reliance class. We have 3 main cable tanks. Just like any other cargo ship, down on the bottom of the ship, the main storage area of the ship. That cable comes up, would travel with some cable machinery, and I'll show you some pictures of that, and then over the stern of the ship. The modern ships are diesel electric. So we've got 5 generators providing us with electrical power. That's powering what we call the hotel services, lights, air conditioning, running the marine sanitation system where we poop. Powering the galley, again, 80 people on board. We're running 4 meals a day. So breakfast, lunch, dinner, and then a midnight meal. So we've got a galley staff of usually about 7 to 10 people. We have a medical person on board just to be able to triage, stabilize, and then we are contracted with a system at George Washington University, a telemedical system. So if they need backup or a second opinion, again, I tell people it's not because they care about us. It's because if we've got to cut the cable and run into port, you know, you just flushed $1 million out the window. So if we can take care of somebody on board and stabilize it and not have to do that, that's why we carry either a doctor or an independent duty nurse or corpsman. We also, again, that little bit dangling off the end there is a ROV, remotely operated vehicle. It's a tracked submarine that can go down to depths of about 2,500 meters and inspect cable. It can bury cable on the seabed using a water jet configuration. It can cut cable. As I said, at times we drag a hook. Sometimes we can send that down. It can cut the cable, and then it can attach a gripper to one end of the cable, eject the gripper from its arm. We attach a rope to that, and we can pick it up to the surface. We can carry, and everybody says, how much cable can you carry? And I said, well, it depends. When are we going to get there? It depends on how fast we go. Again, the cable types that we have, the basic lightweight cable in a modern system is 17 millimeters in diameter. We will likely actually fill up our cubic capacity of those tanks before we hit the weight carrying capacity of the ship. Whereas if we're carrying some of the cable that we install near shore, where you take that basic cable, wrap it with either 1, 2, or 3 wraps of steel wires to protect it from fishermen or ships anchoring, we'll hit the weight carrying capacity of the ship before we hit the cubic capacity. So with straight lightweight cable, we can get close to 7,000 kilometers. In the heaviest of cable, we can get about 2,000 kilometers. Sometimes we hit, and you may have heard this good old seagoing term of full and down. Any cargo ship that was worth its salt would always want to travel full and down, meaning you've filled up the cubic capacity and you're down to the maximum weight capacity of the ship. Are you using it to its full potential? Occasionally we hit that, but sometimes it's all near shore work that we're doing. So it's a heavier cable. Sometimes it's all lightweight cable. So we've cubed out, we've filled up the tanks. Subcom, again, the legacy AT&T, kind of an interesting way that we've gotten to where we are. AT&T never made their own cable. AT&T designed the cable. AT&T installed the cable. They operated the systems. They did the maintenance. They contracted a company in New Hampshire called Simplex Wire and Cable. Simplex Wire and Cable built cable to the AT&T designs. A company called Tyco International bought Simplex Wire and Cable back in the 80s. Early 90s, AT&T decided that they wanted to get out of the physical end of things, the design, manufacture, installation. They just wanted to operate the systems. So they put the division on the market. Tyco International was a conglomerate. Tyco at one point in time couldn't tell you what they did because they did everything. And they said, well, we already own the cable factory. Why not? Let's go ahead and buy the cable laying division of AT&T. So we went from being AT&T Submarine Systems to Tyco Submarine Systems. And then Tyco decided, let me back up. When they bought the company, they said, we do not want to be a cable system owner. We want to be a provider. We want to design, install, maintain, but we're not going to try to get into this competition with the telecoms. The 90s rolled around. Everybody was building cable systems. Tyco, we at Tyco Submarine Systems were extremely busy serving everybody else's needs. Tyco said, hey, wait a minute, we got to get into this. So they spun off. They did an IPO of a company called Tycom. I think we lasted 6 months. If anybody, there's an empty office building right down by Morristown Airport. We called it the Puzzle Palace or the Marble Mausoleum when they built it, because giant, wonderful looking building. I think they were in it for 6 months before they moved back out. Tyco Global Network or Tycom Global Network lasted as long as we could build it. And then the .com boom went bust, and Tyco really didn't have any customers for their system. Along comes an Indian company called Tata. They bought it lock, stock, and barrel. TGN, which was Tycom Global Network, went to being Tata Global Network, still in operation. We no longer are involved in the owning and operation of cable systems. That we learned our lesson. Tycom was bought back by Tyco International. Anybody remember L. Dennis Kozlowski, who was there was a bit in Forbes magazine, what do you call a guy that sold you something for $32 and bought it back for $16 and told you it was a good deal? That was Tycom, because it hit at 32. They bought it back for 16. Essentially, they bought cash for 50 cents on the dollar and sold their network. We were still Tyco Submarine Systems after the Tycom debacle went on. Then Tyco tried to reinvent itself. They split into a multitude of companies, one of which was Tyco Electronics, which then became TE Connectivity, which then just became TE. They had us. We ended up in their division. We really didn't fit. They were a manufacturing division. So what is it now? 3.5 years ago, they spun us off to Cerberus Venture Capitalists. So we are now a wholly owned subsidiary of Cerberus. We're now called Subcom. So that's how we got to where we are. But we're still doing the same thing that was started back in the 60s by AT&T. Where was I going with that? Simplex Wire and Cable, the company that made cable for AT&T, is still making cable for us. They are Subcom, what are they called now? Subcom Technology and Cable. They change names every week. Anyway, up on the river in Newington, New Hampshire, if you've ever been through the little town of Portsmouth, if you go up the river a little further, is Subcom's cable factory. So these cable systems, if we're putting a system in across the Atlantic, the entire system is built in the factory before we start. It's built, all the components are put together, it's powered up. The whiz bangs go through everything and say, yeah, it should work. Because a lot of times it should work. When you take something that was constructed in a factory at ambient temperature stick it on the bottom of the ocean at the pressures that you'll find at 7,000 meters of water depth and the temperatures, it actually affects how light goes through a piece of glass. It actually affects how electricity goes through copper. So I say they say it should work. They've done this long enough. They know exactly how it's going to work, except when they don't. So we pull up to the factory. There are not quite this size tanks at the factory. They're much smaller, but they've got 100 of them. They've got the entire cable system put together. Ship pulls up to the dock. We have machinery on the deck of the ship and we're pulling cable down to the ship. We hire temporary labor up at the factory and they walk in circles for 12 hours a day. And they lay the cable into the tank, make sure that there's no crossovers. It's not going to get tangled up. We've got a ship's officer on duty 24 hours a day. We've got ship's crew on duty down in the tanks with them, making sure it's done properly. And of course, everything has to be marked properly because we've got splices. Again, you've got your car that you bought and it was a Monday morning vehicle. And after owning it for 6 months, you figure out it's a lemon. I'm going to send it back. Monday morning cable is usually in about 10-kilometer segments because there's a lot of quality control going on. When they started on Monday morning, maybe things weren't great. They're running a line of new cable, something happened in manufacturing, and they've got to cut it. So they've got a good 10-kilometer bit of cable, then they get a good 20-kilometer bit of cable. And then the machinery in the factory, your Wednesday afternoon cable, where everybody's feeling good, you're finally over the weekend, the maximum we can do is 80 kilometers. So we get a lot of 80-kilometer sections. They're actually great, especially if our signal amplifiers are only 45 kilometers apart. We can go from amplifier to amplifier with nothing in the middle. Back to Monday morning, those 10-kilometer segments, 6 kilometers, we actually may have splices in the cable that are done in the factory. They end up being about this long, that big around, and they actually get stowed right down in the cable. I don't see one in this, well, there is one, but you can't really make it out. They get stowed right down with the cable. But as we're coming to that, when the cable's coming out of the tank, we want to know where that is because we have to make sure the machinery is ready to pass it through. The other thing is those optical amplifiers that I was talking about are about the same length, a little bit over a meter long, but they're about this big around, weigh about 700 pounds, and can't be stowed down in the tank. So we actually stow them on the deck above the tank. So the cable's being coiled down in to the tank. When we come to an amplifier, it comes up to deck and then back down into the tank. So again, we need to know where those are because when we come to one of those in the installation, it's got to be moved over so that it's able to be deployed through the machinery. This is actually one of the machines that we use to install the cable. This would be at the stern of the ship. This is a factory picture, but it's called a linear cable engine. Anywhere between 18 and 21 wheel pairs, depending on the ship that it's on and who built it. But that actually grips the cable. It maintains tension on the cable and controls the speed of payout. Again, when we first start out, that machine is pulling the cable out of the tank, pushing it over the stern of the ship. But when we get out in deeper water and we're moving along at 6 knots, this just becomes a brake to hold the cable from just pulling out of the ship. So it becomes a braking mechanism, but we use this to control the tension and the speed of the cable as it's being paid out. That's actually the machine installed on board the ship. Again, it's moving along at 7 knots. Those wheels are spinning. Anybody working near the machine, we've got the guards up so that they don't manage to get their hands in the machine. We also have cable drums, which is just like a winch on a sailboat, except it's a horizontally mounted winch. We take 4 or 5 turns of cable around that drum. So it's coming from in the ship, around the drum, and then over the stern of the ship. We use this more for repair work, slower speed work, picking cable up, paying it out. There's actually two side by side. So I mentioned that cable repair earlier, where we may end up with two segments of cable up to the ship. They're horizontally mounted winches capable of pulling about 30 tons force if need be. Again, that's one on a factory floor. So you can see it's just a big sideways mounted winch. I spoke about the equipment we use to bury the cable in the seabed. On the left is what we call a sea plow. Pretty much a farmer's plow that we drag behind the ship. We lower it to the seabed with the cable already in it, lay it down on the seabed, move the ship away from it, lay out a tow wire. We've got a steel tow wire, about 1 3/4 inches in diameter. So we've got the tow wire to tow the plow. We've got the telephone cable going down to the plow. And then it has its own fiber optic control system to control the functions of lifting the skids up, to control the depth of burial, camera systems, sonar systems, tension systems. So we drag that along behind the ship, and it's capable of burying the cable down to about 3 meters into the seabed to protect it from fishermen, ship's anchors, etc. We also have, as I said, remotely operated vehicles for working on the cable, both for burial, cable repair operations. This frame on the front is actually used to sense cables buried in the seabed. It's a magnetic sensor, so the cable has steel in it, especially the stuff that we bury that is wrapped with steel. So it's a magnetic sensor. We can also put a signal on the cable, an electrical signal that can also pick it up with that sensor. So if it's a buried cable and we're trying to find it, that frame can find it. It's got a water jet system, both for burying cable and also excavating anything that's buried that we have to repair. Good down to about 2,500 meters of depth. That's a view of the sea plow moving along the bottom. And this might be a good time, Joel, to just going to show you a quick video from Subcom that's on YouTube. It just shows the entire process from when we start on one shoreline, bury cable, deep sea cable, and pretty much just a soup to nuts quick look at the cable laying process. So we'll back a ship up close to shore. We'll tie floats onto the cable and have a boat pull it close to shore, usually connect a wire to it, some form, either a winch or heavy equipment to pull that cable up into its connection point on shore. That all gets buried. Then the ship starts to move off, laying cable away from the shore. Again, I talked about those system amplifiers. That's an amplifier going down. Actually goes right through the sea plow that we're towing along the bottom. And the ship moving along, we get to the point where we finished the section where we need to bury it. We actually now lift that plow up off the seabed. In this case, they're talking about going over either a pipeline or somebody else's cable. So the plow got lifted up, put it back down. Now we continue to where we're done with burial. Plow comes up to the ship. Then we'll go back. We have to inspect where we buried the cable, make sure that we did it to the proper specs. So here's the little submarine going down, moving along the cable. It can use a water jet system to bury cable where maybe the plow couldn't because it's close to another cable or a pipeline. So a little submarine can actually come very close to that pipeline or other cable and then resume. And then we would go across the deeper spots, again, laying cable as we're moving, another amplifier laid down. One of the things, can you pause it there for a sec? This is just trying to illustrate the topography of the seabed. Seabed isn't perfectly flat, obviously. It looks just like the rolling hills and mountains that we see on land. When we're installing the cable, we want to try to have it lay on those contours. We don't want it suspended between peaks. We don't want to pile up excess cable on the bottom. So when we start out with a cable laying system, somebody says, I want a cable from New York to London. We look at, okay, what's the shortest route? A to B. That would be easy if we just went A to B. And of course, the shortest route on the oblate spheroid we live on, this ball, there's no flat earthers in here, are there? Okay. It's actually a curved, it's a great circle from place to place. But then let's take the middle of the Atlantic. You have something called the Mid-Atlantic Ridge. It's a mountain range in the middle of the Atlantic. Just like driving to California, we try to find a pass where we can, instead of going over the peaks, go through a nice pass through the mountains. So we'll arrange the cable route to go through the passes, avoid things like underwater volcanoes, underwater landslide areas. So all that is mapped out, it's surveyed, we find where the contours are, and then the whole system is designed to make sure that we're laying the cable along the proper route and just have it laying on the seabed on those contours. So that's where this slack management comes in. We want to have enough slack so it's not bar tight, but we don't want it piled up on the bottom. So we keep track of how fast the ship's moving and how fast we're paying out cable. And it's following a pre-programmed system of exactly where we need to adjust that slack. We have a computer modeling system that models how the cable behaves in the water at certain depths and certain tensions. That's being tracked by the cable engineers on board as we're doing this. So slack management becomes key. Data management, where did we put the cable? What were the tensions? What was the depth? So when we're done, we can present a quality record to our customer and saying, your cable went in the right spot and we did the best job possible and nothing's ever going to go wrong with it. We hope. But that's just what they're trying to illustrate there. Things do go wrong. Sometimes you find out, in one case in the Red Sea, there was an active underwater volcano that we got a little too close to. It melted the cable, had to go back, recover it, reroute around it. It wasn't active when the survey was done. Taiwan, right off the shelf of Taiwan, it gets very deep and it's a very earthquake prone area. So we found out that that's not the best place to put cables, but unfortunately there's a lot of cables that run right through that area. So if there's an earthquake in Taiwan, wait a couple days and you'll probably find out that there's been an undersea landslide and it's wiped out a cable. Those are really a pain in the neck to deal with because sometimes that landslide might be 30 or 40 kilometers long and now it's buried a section of cable that we can't get to. So we may have to put in a whole new 40, 50 kilometer section of cable because we can't find the cable that was there. But that's just what this is illustrating. We keep track of the slack as we're going across the seabed. So that was just a little quick look at how we do things. Yeah. I talked about the who, the traditional telecoms, Google, Facebook, Amazon. That's the slideshow. I see hands already. Any questions? First.
We'll manage the Q&A, but I already told Joel I want to ask the first question.
Okay, well, proximity to the mic.
That's right, I get control. First of all, I just want to thank you so much for coming. And given where we are at this moment, just 2 miles down the hill from Bell Labs and Murray Hill, not surprisingly, Ian is exactly right. We have lots and lots of retirees from Bell Labs and other components, AT&T and fragments thereof, and even plenty of guys who worked on either developing fiber optic technology or undersea cable technology, even in this room, and the rest of us we're seeing this all developing around us and we're fascinated by it, but never heard all the details before. I mean, this is fascinating to me. I just really love it. I was going to ask a question about the amplifiers. It's kind of late and other people have questions too, but just a quick one. When you amplify a light beam in a fiber, is that a point where there's latency, or do they meant, so it's all of these points of amplification where the latency comes in?
That's one of the areas. If we back up to 1988, the first fiber system across the Atlantic, the early fiber systems actually had repeaters.
Yeah,
So
Yeah, that's-
same housing, they look identical, but the signal came in light. It was
Okay.
dropped back to an electronic signal.
yeah,
There were actually lasers in those systems, and then it was fired off again.
yeah, there's
Couple
clearly
big problems.
electronics, yeah.
If that component failed, your system was done. It shut down. The other problem was, everybody remember the 286, the early Intel processors, they ran at a certain speed.
Yeah.
Each of those amplifiers ran at a certain speed. So even if you got a better signal processor at either end, you couldn't speed up or increase the capacity without going and changing all the repeaters. They developed the optical amplifier. The optical amplifier, the signal comes in light. And this is where the black magic happens. They take, and there's, as you were just saying, there's probably people that could explain this better than I, even in the room, but they take a specially coded section of glass fiber, excite it with electricity, boost the signal in light, and send it off again. And it's even been explained to me that anytime you boost a signal, you're going to introduce noise. One of the things that the whiz bangs did is they boost the signal and they get a boost in the area where they want the signal, and they get the noise in an area of the light wave that doesn't affect anything. So it's not something for nothing, but yes, each one of those amplifiers does introduce some of the latency.
Yeah.
It's also just movement through the glass itself. And then again, I talked about the whiz bangs and designing the system. And when it's in the factory, it's going to work as if it's in the bottom of the ocean. A couple of the much higher capacity, much lower latency systems we've done recently, we've had to stop during the installation system, record a bunch of data, send it back to the whiz bangs, let them chew on it, and then come back and say, put this component in. So there's actually filtering components that we'll put in the system and until the system is on the bottom and operating, they won't know exactly which one to put in. And again, that's one of those on-time things. You call the whiz bangs on Friday afternoon and say, we're here. And they go, we'll get back to you on Monday. And we go, no, you won't. And they go, yeah. Somebody calls their boss and they're there Friday night. So that is the components, and even the processing of the signal does add some of the latency.
But I'd really like to start with Alan Chenoweth, because he was a technology guy who ended up as a senior executive in the Bell system, and he has a lot of insight into these things. So Alan, could you start?
Oh, thank you, Paul. Yeah, that was a fascinating talk, and my goodness, my memories stirred my memories, which actually go back to 1956, when the celebration over the laying of the first telephone cable, but later much involved with the development of the devices and fibers that were going into TAT8. I remember that TAT8 was a challenge to us in the technical world, to which I compared with President Kennedy's challenge to put a man on the moon. It was, long lines challenged us, and we didn't really know how to do it at the time. But I do remember we had to develop devices which statistically would have 100-year lifetime, because you didn't want, the original plan was to make the TAT8 have a lifetime of 20 years, maybe it was 30 years, I thought 20, but and to allow for 3 grapplings, 3 repairs during its lifetime. That was the economics of the system, and to keep those repairs down to a minimum, we had to sort of be confident that the device lifetime, for example, was 100 years. And how do you guarantee 100-year lifetime? How do you do a life test to guarantee that? That was a big headache at the time. So I found that a really fascinating story. And one question. I seem to remember some tales of the Soviets dragging up the early cables to find out what we'd constructed to put down there. Do you know if there's any truth to that?
I'm not sure they did much with the commercial cables. If anybody ever wants to read a very interesting book called Blind Man's Bluff, which was some of the government cables. And again, there might be some people here from Bell Labs that can't talk about this because they weren't allowed to, but Bell Labs actually developed a system to tap in to some of the Soviet military cables and vice versa. I think they were playing around with some of our military cables. Commercially, there is a great fear that some of these data centers could be crippled by a bad actor coming through with a set of grappling hooks and wiping out 4 or 5 systems at once, to the point where the US government actually has a program right now called the Cable Subsidiary Program. And this is just a recent development in the last couple of years, but the US government pays Subcom to keep a couple ships available should there be a rush need to repair a bunch of commercial cables or even military cables that may have been wiped out by some bad actor. So in answer to the Soviets stealing commercial, I'm sure they probably did. We know the Chinese did and still do. They actually bought Cable and Wireless, one of the British companies, and have basically gotten a primer on how to install cable systems.
Hi, Griff Smith, Bell Labs alumnus. How did you get the power across the Atlantic? That seems like a really long run to try to power all those amplifiers.
Well, the power feed equipment in either shore station is usually designed as such that they're powering from either end. So they're powering electrically from either end, and there is a null point in the middle somewhere. Cable systems, generally the older systems were running at about 5,000 volts, 1.5 amps, so a good bit of power. One of the problems we have with the cables, if there's a fault, if something hits the cable, a fisherman, a lot of times all it's doing is cutting through and getting to the copper, and it then grounds to seawater. In some cases, they can continue actually powering to that cut point, keep the system operating until we can get out to repair it. But it is a good bit of power from either side. So the power feed equipment, that's a whole specialty on its own as part of the technology that keeps the systems running. The ships themselves are equipped, again, with power feed equipment to power the system while we're installing it and also while we're testing it.
Well, let's hear from the world sailor, and he's a visitor too.
My question is, at what point does the catenary weight of the cable or the ship's momentum and whatnot would snap a cable like that?
Well, again, the basic cable right there will break at about 20,000 pounds of tension. So we're constantly monitoring that tension. So as long as the ship's moving, we're paying out cable, we're watching the tension. Usually we're running at about 5,000 or 6,000 pounds of tension when we're laying in that configuration. If we stop, and I'm trying to think, it's one of those figures I should have off the top of my head, but a kilometer of that cable weighs about 4,000 pounds, I think. So kilometer of that stuff, no, sorry, kilometer of the lightweight weighs just under a ton. So it's about 1,800, 1,700 pounds. So if you have 25 kilometers out, it's in suspension, but it's also only sinking at a certain rate. There's a hydrodynamic constant to that cable. So as we're pumping cable into the water, it's sinking at about a knot as it's going down. We're moving the ship out. We're watching the tension at the surface. All's good. If we suddenly stop, now we've got 25 kilometers out, we will quickly exceed the breaking strength of that cable. So that's when we start backing down at the sinking rate of the cable. It's only going to sink so fast. Back down on it and lay it out, let it start laying on the bottom. Does that answer the question? Okay, yeah.
Okay, here.
Harry Hines, do you still use ships just to do the continental shelf, like the Dock Express 20? I was on it.
Oh, you were?
Yeah.
Okay. The Dock Express 20. The DE 20, as we call her, was a Dutch heavy lift ship originally developed to float other vessels on, float up out of the water and transport them across the ocean, either for repair, yacht movement. Dock Express is huge into yacht movement now. They're still operating a lot of those other ships. The DE 20 was a ship that AT&T chartered and was using for nearshore work with a sea plow. We actually kept her on charter, and Dockwise actually built 2 purpose-built cable ships at the beginning of the 2000s. So we had 3 Dockwise ships up until about 2002. In answer to your basic question, in some areas, we still will use a separate vessel to do the nearshore work. Depending on the availability, where we are in the world, the depth of burial, the tools that are available, and the overall need in which we need to get that system installed, it might behoove us to charter a vessel to do just the nearshore plow work while we've got our deep sea capable vessels doing the higher speed stuff across the greater expanses. The system that I was just working on off the coast of India, in the Mumbai area, it was very shallow, so we couldn't get the mainlay ship close to shore. So we actually chartered a barge to do out to the, and it was also a customs issue, charter an Indian barge to do the work within the Indian territorial sea out to the territorial sea line, where the mainlay ship then spliced into it. In Sri Lanka, same thing there. We had a barge do the section out from there. The other coast, in Chennai, we were actually backing the mainlay ship right up to the beach and doing a direct landing and launching the sea plow close to the beach. So we still do use third-party vessels for some of the specialized work.
Thank you.
Online, Tom Forger.
Yeah, you mentioned you had amplifiers. What is the power source for the amplifiers?
Actually, either end of the cable system. So some of these, if it's a point A to a point B, there's a power station at the cable station on either end, powering from either end. Some of the more complex systems where there might be multiple landing stations with what we call branching units along the way, where we actually have the cable come and then split off into a fork, as Yogi Berra said, when you come to a fork in the cable, take it. But splits off in different directions. You may have 5 or 6 landing stations in one cable system. Each one will have a power source powering that segment. Sometimes they're powering multiple segments from the power sources.
Okay, this is the last question.
Hi, Dave DeLong. In sea lanes or even on the high sea, is there questions of right of way, or do you have some special treatment?
Yeah, get out of my way. We are, as we're operating according to the international rules of the road, we are a vessel constrained in our maneuverability. So if there's another vessel coming along and they're unencumbered in any way, it's their duty to get out of our way. Does that mean that they always do? No. We are obviously keeping track of all vessels around us, but there's a hierarchy. Power-driven vessels that are unencumbered, vessels restricted in their ability to maneuver, vessels not under command, fishing vessels in certain areas. And again, just quickly touch on fishing. As I mentioned, we bury the cable in the seabed. In certain countries, the fishermen have to mind where the cables are. And if they hook a cable, they're going to pay for the repair if they break it. US is one of those countries. So if a fisherman hooks a cable, all the cable system owners have probably gone to the local fishing ports, Barnegat Light. I know for a fact they've gone there. They've distributed information. They say, if you hook a cable or you think you've hooked a cable, stop, call us, cut your gear away, and we will pay for your gear. Japan, if a fisherman hooks a cable and he loses his gear, the cable owner's paying for it. So we really have to be careful of burial in the seabed, how deep it's buried. In certain areas, we have to make sure the fishermen don't hook it because they have more rights than we do. In certain areas, fishing boats have more rights than we do when we're laying cable, so we've got to get out of their way. But the basic answer to your question is we are restricted in our ability to maneuver. We're broadcasting a signal that says that by voice and by automatic identification system, as well as showing lights so they can look at the ship at night and say she's restricted in her ability to maneuver, and certain shapes during the day so that they can see right off the bat that we can't move quickly.
Very much, Captain Carl. It's a wonderful presentation. Wonderful presentation. We appreciate it very much. And we have two ways of thanking you for your consideration. And the first is an official certificate from the Old Guard with an orchid on it, which is our logo, due to the fact that Summit was the orchid capital of the world at one point back in 1930 when we were formed. And so we present this to you. And the second is with the Old Guard salute.
Thank you very much, and my pleasure. Hope you enjoyed.